Welcome back, everybody. We're diving into a paper today that could really shake things up in the software development world.
Oh, yeah, for sure.
It's all about Minimax 01, right?
That's
This new foundation model
Yeah,
built just for us software engineers.
exactly. And this is not just another LLM.
Okay.
The team behind Minimax 01 really wanted to fix this problem we all deal with every day.
I think I know what you're getting at.
Yeah.
Limitations of context windows.
You got it.
So for those who haven't run into that term before,
Sure.
can you give us a quick breakdown?
Absolutely. So picture this. You're trying to debug this huge program, but you can only see a teeny tiny bit of code at a time.
Okay.
That's basically what most language models are doing right now. Their context window, the amount of info they can process at once, it's pretty small.
So they can't see the whole picture.
Exactly. They miss those connections and dependencies between different parts of the code.
And that's where Minimax 01 steps in.
Exactly. This model has a crazy context window of 1 million tokens.
Whoa, 1 million.
It's like 750,000 words, to give you an idea. Most models today top out around 256,000 tokens.
So this is a huge jump. How'd they pull that off? The paper mentions something called lightning attention.
Right.
What's that all about?
That's one of the big things that makes Minimax 001 so special, this lightning attention.
Okay.
It's a much more efficient way to deal with those long strings of data. Basically, it lets the model process information in linear time and space, which is super important when you're working with 1 million tokens.
Okay, for us software folks, linear time and space, that means faster and less memory.
Yes, exactly. It's like having a compiler that can look at your entire code base all at once. That's the kind of efficiency we're talking about. The old attention mechanisms get really slow and resource heavy with long sequences, but lightning attention keeps everything moving fast.
It sounds really useful for stuff like code analysis and refactoring, where you got to understand how all the parts of a large code base fit together.
Exactly. And it's not just speed. Lightning attention also helps the model see those long-range connections within the code, giving it a deeper understanding of the whole structure and logic.
I see, I see. Now, the paper mentions a hybrid approach.
Right.
So they're not just using lightning attention.
Right. They're not just using lightning attention. They've actually mixed it with the classic softmax attention. They use softmax strategically for every 8th transformer block.
Interesting. So they're picking the best tool for each part of the model.
Exactly. They're balancing things out. Lightning attention does most of the hard work, but that softmax attention is sprinkled in to make sure nothing important gets lost along the way.
Okay, so we got lightning attention for speed and efficiency. But then there's another piece to this. Mixture of experts, or MOE.
Right.
Can you break that down for us?
Think of MOE like this. You've got a whole team of expert developers, each one a pro in a specific area. You wouldn't ask your database whiz to review your front-end code, right?
Right, of course not.
So instead of using all of its parameters all the time, Minimax's 01 can pick and choose just the right experts for whatever task it's doing. This lets the model get really huge. We're talking 456 billion parameters without bogging down the computations.
It's like having this superpowered dev team on call, ready for anything you throw at them. But all this computational power is useless without good data, right? What did they feed this thing?
They were super careful about the data they used. They focus on 3 things: quality, formatting, and mixing strategies.
Like true engineers.
Exactly. They broke the problem down systematically and tested everything carefully.
Let's start with quality. How do you make sure you're training a model like this on top-notch code and documentation?
Well, they used a model they built before to check each document, making sure things were clear, had enough depth, and were actually helpful. Like an automatic code review, but for the data itself.
That's a cool way to use AI to help get the training data ready. But what about formatting? How do they organize the data for a model that has to understand both code and regular language?
They knew that different types of data need different structures. For example, dialogue data is organized differently than code or documentation. So they made special templates to keep things consistent and clear, but they made sure to keep the natural language patterns of each type of data intact.
It's like picking the right data structure for your program. You wouldn't store a list of numbers in a binary tree.
You got it. Right structure for the right data. And lastly, they looked at data mixing strategies. It's not just about having good data, it's about having the right mix.
So just like a good software team needs a balance of skills and perspectives, the model needs a balanced diet of data.
Exactly. They started with a uniform distribution across their corpus, but then tweaked the sampling weights to favor the high-quality stuff. But They didn't ditch the lower scoring content entirely. It's like realizing that even average code can sometimes teach you something valuable you can learn what not to do.
That's a great point. Now, I got to ask, how do they train this thing on a million tokens? That sounds crazy computationally expensive.
Oh, it was. They had to get creative to avoid all that waste from traditional padding techniques. Imagine padding a million token sequence.
Yeah, it'd be like reserving a whole stadium for a tiny dinner party.
Right. They needed a way to cram as much useful info as possible into each training batch without wasting resources on padding.
And that's where data packing comes in. You mentioned it earlier. But can you unpack that a little more? I'm still not quite getting it.
Think of it this way. You've got all these code files, different lengths, right? Instead of padding each one to the max length, they just string them together end to end, making one long, continuous stream of tokens.
Ah, so it's like combining all your code into one massive file. That's clever. Less wasted space.
It is. And data packing doesn't just save space, it also cuts down on wasted computation during training. They're making the most of every GPU cycle. And when you're working with datasets this huge, that's super important.
Smart. But handling a million tokens at once, even with data packing, got to be a challenge. What other tricks do they have up their sleeve?
Well, that's where things get really interesting.
All right. And we'll dive into that in the next part of our deep dive.
Ooh, now you've got me hooked. I can't wait to hear more about how they tackled this engineering feat.
Yeah, you're right to be curious. Training a model this big with a million token context window, it's a huge project. Like building a skyscraper, got to have a solid foundation, a well thought out structure.
So how did they lay that foundation? What were some of those key architectural decisions?
Well, right off the bat, they had to figure out how to train a model with such a long context window without, you know, breaking the bank computationally. Traditional padding techniques would have been way too inefficient.
Yeah, like reserving a whole football stadium for a small dinner party.
Exactly. They needed to squeeze as much useful information as possible into each training batch without wasting precious resources on padding.
And that's where data packing comes in, right? We talked about it before, but I'm still a bit fuzzy on how that actually works. Okay, so imagine this. You've got a bunch of code files, all different lengths. Instead of padding each file to the max length, they just cleverly string them all together, end to end, making one long, continuous stream of tokens.
Ah, so it's like combining all your code into one massive file.
Yeah,
Less wasted space. That's pretty neat.
it is. And this data packing thing, it's not just about storage. It also cuts down on wasted computation during training. They're squeezing the most out of every GPU cycle, which, when you're working with datasets this massive, is super important.
So they've optimized the use of resources during training. But what about the model architecture itself? How do they handle combining lightning attention, softmax attention, and mixture of experts? That sounds pretty complex.
Yeah, that's where their parallel processing skills really come in. They had to rethink how they parallelized the whole training process to make it work with this complex architecture.
Okay, parallel processing. We software engineers deal with that all the time, right? Distributed systems, speeding up build times. How do they apply those ideas to training a huge language model?
They came up with some really clever strategies to spread the workload across multiple GPUs, and they had to optimize the communication between different parts of the model.
Sounds like they're treating the model itself as a distributed system, breaking it down into smaller, manageable chunks.
That's a great way to put it. That's exactly what they did. They developed something called expert parallelism to optimize communication between the different experts in that MOE layer.
So instead of having all the experts trying to talk at once, they have their own dedicated channels for smoother, more efficient collaboration.
Exactly. It's like a well-run team meeting where everyone gets their turn to speak without interruption. And to split up the work even further, they used expert tensor parallelism.
Okay, expert tensor parallelism. Now that sounds pretty technical. Can you break it down for us non-experts?
Imagine you have this huge matrix of data that needs processing. Expert tensor parallelism lets you split that matrix into smaller pieces and distribute them across multiple GPUs, so they get processed in parallel. It's like having a team of workers, each putting together different parts of a car, all at the same time.
Ah, so it's like a distributed build system for code. Each GPU is compiling a different part of the project.
You got it. And these parallel strategies, they're essential for training a model of this scale efficiently. But they didn't stop there. They also had to optimize the inference process, how the model actually generates responses after it's trained.
Right, inference. That's crucial for real-world applications. You don't want to be waiting hours for a code suggestion or a bug fix.
Absolutely. So they implemented a bunch of clever techniques to speed up inference. One of them is batched kernel fusion.
Now that sounds intimidating. Batched kernel fusion, like something out of a sci-fi movie.
Don't worry, it's not as complicated as it sounds. Think of it like this. You have a bunch of tasks that need to be done one after another. Batched kernel fusion lets you combine those tasks into a single optimized operation, so you reduce overhead and get better efficiency.
Okay, so it's like combining multiple database queries into one optimized query. You make fewer trips to the database, which makes things faster.
Exactly. They're streamlining the whole computational flow, cutting out unnecessary steps. They also separated the pre-fill and decoding execution processes so they can handle mixed inputs more efficiently, like having separate pipelines for processing different types of data, each one optimized for that specific task.
So they're going for both speed and flexibility. Impressive. But what about handling those super long contexts during inference? You mentioned the model can extrapolate up to 4 million tokens. How does that work in practice?
That's where their improved linear attention sequence parallelism comes in. They call it LASP plus A.
LASP plus A, another acronym. But before you explain that, can you remind us what linear attention means here?
Sure. Remember how we talked about lightning attention being a more efficient way to handle those long sequences? Well, linear attention is what makes that efficiency possible. It lets the model process information at a cost that scales linearly with the sequence length instead of quadratically.
Right, so with linear attention, if you double the sequence length, the processing time doubles. But with the old attention mechanisms, the time might quadruple, or even worse.
Exactly. That's why linear attention is so important for handling those super long contexts. Now, LASP Plus takes that efficiency a step further by parallelizing the attention computation across multiple GPUs.
So they're breaking down the attention calculation into smaller pieces that can be processed at the same time.
Precisely. LASP Plus is designed to handle those super long sequences efficiently. They also introduced the Varlin feature. This helps optimize the processing of variable length inputs. Remember data packing from training. Well, the Varlin feature lets them handle those packed sequences during inference without any problems.
So it's like having a dynamic memory allocation system for your code. The model can adjust its memory usage based on the size of the input, which is super efficient.
Yes, exactly. All these optimizations come together to create a lightning-fast inference engine. They achieved over 75% model flops utilization, or MFU, on the NVIDIA H20 GPU.
Okay, MFU. I'm not familiar with that one. What's that measuring?
Think of MFU as a measure of how well the model is using the hardware resources. A higher MFU means you're getting more out of your hardware, which, when you're running these big models, is crucial. It's like getting better gas mileage with your car.
Got it. So they're not just throwing more hardware at the problem. They're making the most of what they have. That's true engineering.
Absolutely. And that's what makes Minimax 01 so groundbreaking. It's this awesome combination of cutting-edge research and clever engineering.
It's clear that they put a lot of thought into every aspect of this model. The data, the training, the inference optimizations. It's like a well-designed software project where everything fits together perfectly.
Couldn't have said it better myself.
All right, so we've covered the technical details of Minimax 01. We've seen how they've tackled the challenges of training and running a model with a 1,000,000 token context window. But now I want to shift gears a bit and talk about what this means for us, the software engineers. You hinted at some pretty amazing possibilities earlier, like AI-powered code completion and debugging tools.
Yeah, let's get into that. I mean, what's the point of all this innovation if it doesn't actually help developers?
Exactly. So let's explore how Minimax 01 could change the way we write, debug, and even think about code. Okay, so let's start with code completion. I mean, we all use it, right?
Right.
And we all know how annoying it can be when the suggestions are just way off. How could Minimax 01 make that better?
Well, imagine having a code completion tool that doesn't just suggest the next word or a function,
Yeah.
but it actually understands your whole code base. It could recommend entire code blocks or functions based on what you're trying to do, not just what you typed in the last few lines.
So it's like having a senior dev looking over your shoulder and being like, hey, I think I see what you're going for here.
Exactly. And because Minimax 01 can handle those really long contexts, it could even suggest code from different files or modules. You wouldn't have to keep jumping around trying to remember where you saw that perfect function.
That would be a lifesaver, especially for those massive projects where you're switching between files constantly. What about refactoring? Could Minimax 01 help us write cleaner, more maintainable code?
Oh, absolutely. Refactoring is all about making your code better without changing what it does, right?
Yeah.
And Minimax 01 could be a game changer. It could analyze your entire code base and suggest things you might never even notice on your own.
So it's like an AI-powered code linter that's not just looking for syntax errors, but actually looking for ways to make the structure better.
Exactly. It could find places where you can simplify a function, remove redundant code, or even improve how your classes and modules are designed.
And because it gets the big picture, it could even see how a change in one file affects others, right? No more, oh, I changed this one function and now something else is broken.
Exactly. It's like a safety net, catching those potential problems before they happen. You could refactor with confidence, knowing the model is checking for unintended consequences.
Okay, now let's talk about the thing every developer dreads, debugging. We spend way too much time hunting down those bugs. How could Minimax O1 help us squash them faster?
Debugging is often like trying to find a needle in a haystack.
Yeah.
You're looking at tiny bits of code, trying to find the problem. But Minimax O1 could potentially look at millions of lines of code all at once, looking for patterns and anomalies that tell us exactly what's causing the bug.
So instead of stepping through code line by line, it could just say, hey, the problem is in this function on line 235.
Well, it's not quite that simple yet,
Okay.
but that's the dream. Imagine explaining your bug to the model, and it goes through your whole project, finds the likely cause, and even suggests a fix.
That would be incredible. Like having an AI pair programmer who's always watching for problems and knows exactly where to find them.
Right. It could completely change how we debug, from reactive to proactive.
Love that. Now, something else that eats up a ton of time, documentation. Going through pages and pages of technical docs can kill your productivity. Could Minimax O1 help with that?
Oh, for sure. Imagine asking a question in plain English, and the model goes through tons of documentation and finds the exact answer you need.
Okay.
No more searching through pages or trying to figure out all that technical jargon.
It would be like having your own AI assistant who's read all the docs and can instantly tell you what you need to know.
And it's not just finding stuff. Minimax O1 could even summarize complex concepts or explain them in a way that's easy to understand.
So it's like having an AI tutor who can guide you through a new API or framework.
Yeah.
That's mind-blowing.
And it's not just about code and docs. Minimax O1 is actually part of a family of models. There's Minimax VL01, which is a vision language model. It can understand both code and visual information.
So we're talking about AI that can see and understand code, images, videos, the whole package. What can we do with that?
Think about user interfaces.
Okay.
Minimax VL01 could analyze a UI design and automatically write the code behind it, or even suggest design improvements based on best practices and accessibility.
So we're looking at a future where AI helps us design and build better software, both in terms of how it works and how people use it.
Exactly. And this is just the beginning. The Minimax team is constantly pushing the limits, and I'm super excited to see what they do next.
Me too. This has been a fantastic deep dive into Minimax O1 and what it could mean for the future of software development. To all our listeners out there, what excites you the most? How do you see this technology changing how you work? Thanks for joining us. And until next time, keep coding, keep learning, and keep pushing those boundaries.